Today we're going to look at the final way to calculate enthalpy changes for a chemical reaction using bond enthalpies or bond energies. Okay, and so one thing that we have to do is remember our energy diagrams and they mean. And so remember that when we look at an energy diagram, if we have this, we know that there is a peak, right? That's transition state. And we know that we have some energy that we have to put in. We call that energy activation energy. We know this. And we know that activation energy is the energy required to break the bonds of the reactants. Right? So we know that here we have to put in a little bit of that energy to break those bonds. Now, we also know that bonds get formed when we make our products, right? And so this arrow over here coming down, we know that's the energy released when bonds are formed. And we talked about that, right? Bonds are forming. And so depending on how much energy gets released, right, that reaction is either going to be endothermic or exothermic. So in this case, delta H is negative because it's exothermic, and so we can see that. In this case here, hey, more energy was released when the bonds are formed than was required to break them at the start. And so really, if we're looking at that, we know that delta H is going to be equal to, really, if we think about this, the bond energies of our reactants minus our bond energies of our products. Now this is slightly different than our heats of formation, because heats of formation were products minus reactants. Here we have to have our bond energy of our reactants, and remember that is our activation energy. So basically it's our activation energy, right? Minus the energy formed when bonds are created, or the energy released when bonds are formed, right? And so activation energy minus that energy. So reactants minus products when we're using bond enthalpies. That's really important. That's one thing that people get mixed up. So make sure you're trying to drill that in the head. It's the only time in this whole unit that we will go reactants minus products. Everything else that we do, including heats of formation and some other things, will be products minus reactants. But this is the only time that we do reactants minus products. So make sure you keep that in mind. So how does this work? Well, if we kind of look at our example here, we have CH4 plus O2 going to CO2 plus H2O. And we know that this, in this particular case, we have this reaction. We know it's going to be exothermic because it's a combustion reaction. But in order to use bond enthalpies, one thing that we have to be able to do is we have to draw the Lewis dot structure. So if you kind of need a refresher, go back and review how to draw Lewis dot structures. But just quickly, if we have CH4, we know CH4 looks like this plus O2. Now we have two O2, right? And so we're going to talk about this, but O2 right, has a double bond between it. If we kind of draw the Lewis dot structure, we know CO2 is going to be like this. And then we have two H2O, so we kind of think about it this way. We have this, two of those. So just drawing out the Lewis dot structures for those things. Now, The great thing about this now is that on page 304 of your textbook, right, there is a lovely bond enthalpy chart, right? So they're just looking at the different and various bond energies of things. And so what we can do then is to use this to calculate the bond energy. So if we look here, we have CH4, right? And so if I want to calculate delta H for this, now I'm just kind of doing, okay, well, what bonds do I have and how do they look? And so now in this case, if I think about this, I'm going to look at this and I have 1, 2, 3, 4 CH bonds, right? So I have, right, I have 4 of the CH bonds. And that's got to be plus, and then I have 1, 2 of those, and that's 2 of the O double bonded O bonds. And then from there, I'm going to subtract that because, again, I'm looking at reactants minus products. So now I have CO2, and so now I have 1, 2 of those CO bonds, and so now I have 2 of the C double bonded O, and then I have plus, and now I look, and then I have 1, 2, 3, 4. I have 4 of the OH bonds or HO bonds, however you want to look at them. Okay, so that's what I have. So now those are the bonds that I have. These are my product side. Again, reactants minus products for this thing. And so now I can sit there and say, okay, well, let me fill in the numbers. So now my delta H is going to be, okay, 4 times, now I can come down here and look for my CH. Ooh, there's my CH. So it's 4, 1, 3, right, plus 2 times, and then here is my bond, there, 4, 9, 5, minus 2 times my CO, and I see CO, but I also see this little star here. And when I look down at the bottom, it says, hey, when you have a CO bond as a part of CO2, each individual bond enthalpy is 799. So that's going to be 799 here, plus then 4 of my OH. And so I'm looking, here's my OH, and that is 4, 6, 7. Okay, and so now, again, just working that out. So now 4 times, I forgot to do this beforehand. This is going to be 2642, right, minus, and on this side we got 2 times 799 plus 4 times 467, and that's going to be 3466, and that's going to give us negative 824 kilojoules. All right, so delta H for this process would be there. Now, bond enthalpies are great. They work really well. A couple caveats to it. Number one, you'll notice that they're all in gases. And the reason why they're all in gases is because we don't have to worry about intermolecular forces. Intermolecular forces are going to take more energy to break, and so it's going to be, bond enthalpies are harder to use. And so when we use bond enthalpies, we want to make sure that each substance is in the gaseous state so we don't have to worry about those intermolecular forces. And so because of that, bond enthalpies will give us kind of a rough estimate about where it is. I mean, heats of formations are much better in terms of predicting and actually calculating what the bond enthalpy would be. What the enthalpy change will be for a reaction. Bond enthalpies are good, but they'll give you that general kind of sense. All right. So bond enthalpies, that's what we can do, and that's how we use it. Just a couple things that will make your life a little bit easier as you move through this thing to remember when you're drawing Lewis dot structures, especially if we have our diatomic elements, right? We know Cl2, no, let's just do it the right way. So we kind of go, we have H2, N2, O2, F2, Cl2, Br2, and I2. And if we look at this, right, to remember that, okay, that's a single bond. N2 is held together by a triple bond. O2 is held together by a double bond, as we just saw. F2 is held together by a single bond, as is Cl2, Br2, and I2. These two are the ones to remember, right? You don't have that single bond, you have that triple bond or that double bond. All right, so go back and review how to draw Lewis dot structures, and then let me know if you have any questions. And make sure you're trying to answer the questions for the assessment for today. All right, guys. Hope you had a great weekend, and we'll see you later on. All right, peace, love, happiness. Thanks for playing.